go very, very close to the mean, will be very similar to the linearization, to what the linearized function would do. If they go further away, then you're better. If you're too far away, then it can actually get worse again because you're kind of away from you're not anymore in the kind of meaningful area of your distribution. Okay, just to summarize this everything which is here was on these slides before. This was how to select the sigma points. This is a strategy for how to select the weights. And then we are ready to go. And now just one single slide on how to select the parameters. So this is a parameter suggestion which comes, or not suggestion, the parameters according to the scaled uncentered transform. The scaled uncentered transform is a generalization of the uncentered transform, which has some nice properties. And I use the parameterization here as it is also used for the in the scaled uncentered transform. So the alpha value that we've seen before is a value between 0 and 1. So it can take 1, but shouldn't take 0. So between the open interval here, between 0 and 1. If we have Gaussian distributions that we put in, the beta equals 2 is what we are going to have. If our function has other properties, the transformation leads to higher order moments, this parameter b may not be 2. You can adjust that to other values. But I don't want to go into the details on how to kind of tweak the parameters because actually it's also not too trivial, and I also don't have that much experience with tweaking those parameters. And then we have our term lambda. The lambda, again, depends on this value alpha. It depends on n, and the value kappa. You can choose any value bigger or equal to 0. N is a dimensionality. So it's kind of a strategy with which you can set all your parameters that you need to set, and then you can apply the uncentered transform. Now just some examples to give you a little bit of an intuition what happens if you change these individual parameters. So if we, on this slide, I set kappa to 3 and just varied the value for alpha. So if alpha is very small, all those points are in this plot indistinguishable or nearly indistinguishable from the mean. So the smaller alpha gets, the closer those points move towards the mean. And the larger lambda gets, the further those points move away from the mean. So you see from 0.01, 0.1, 0.25, 0.75. So they move outside. Okay. We can also, and a similar effect is given if we kind of fix alpha and simply vary the value of kappa. So they actually both work in a similar way. The higher kappa get, the more those points actually move to the outside or even far outside the 2 sigma bounds, which are actually plotted here. But again, these are free parameters, and you can choose, some of the parameters you can choose freely, will get the same results, and some parameters you can optimize if you have some background knowledge about the function that does the mapping with function g. But that's kind of, don't want to go into the details of setting these parameters. Okay, so what we've seen so far is the uncentered transform. It's just kind of, this is the basic that we need in order to derive the uncentered Kalman filter. And what I would like to do now is to use the extended Kalman filter algorithm that we had before and kind of change it so that we end up with the extended Kalman filter. So as a reminder, that's what our extended Kalman filter looks like. I hope you still remember that. And what I want to do now is kind of change this algorithm so that we end up with the uncentered Kalman filter. And we'll start with the prediction step, modifying the prediction step in order to have not use the Taylor approximation or linearization by the Taylor expansion, but the uncentered transform in order to come up with using the uncentered transform to compute the predicted mean and the predicted variance. So we try to fix this, kind of get rid of the extended Kalman filter, go to the uncentered Kalman filter. And the first thing we now need to do is actually replace those 2 lines, line 2 and line 3 of the extended Kalman filter, with the line that we need for the extended Kalman filter. And I would like you to do that now, together with me on the blackboard. So what do we need to do in order to realize those 2 steps? You can cheat if you look up the slides on the web, but you can also use your brain to do that. Yeah.
You calculate the mean as
So first, we need to define our sigma points, kind of the first step that we're going to do. So we say we have our mean at t minus 1, and then our mean at t minus 1 minus some, whatever, gamma times the square root of t minus 1, sorry, plus minus 1, and the same, or let's say plus minus. Then we have our sigma points. What do we need to do next?
Use our nonlinear function of these points.
So we, let's say, take y, t is a set of points where every individual point, or we can actually do that directly, the mean. Save a little bit of space. So we want to compute then directly the mean, t, the predicted mean, this guy over here, is given by the sum from I equals 0 to 2n, and exactly summing over the weighted transform points. So our weights and g x I. It's written like this. And then we have our transformed mean. What do we do with the covariance matrix? Exactly. So what do we need to do here? How do we compute a covariance matrix? Again, from 0 to 2n. Okay, well, wait. How are we going to do that? Yeah.
the point x I minus the mean.
It's a transform point.
The transform point.
All right, yeah, exactly. Minus the mean, predicted mean.
Times that transpose.
Yeah. Transposed. Am I done? So that's what the uncentered transform tells us. We're done with the uncentered transform, but there's something missing in the Kalman filter step. If we execute a prediction step, we increase our uncertainty. In which way do we increase our uncertainty? Or why do we increase our uncertainty?
Plus some error.
Yeah. Plus our RT, which was a motion noise. Because we expand our the covariance matrix by this term.
Sorry.
Yep.
Question, why summing up to 2n, not 2n plus 1?
Because you start from 0, I equals 0, to 2n, and then you have n, 2n plus 1. But we take into account all sigma points. Yeah. And that's exactly what we've written down here. The only difference is these points have been transformed, so we kind of move this guy into directly in here. But of course, if you would implement that, you wouldn't execute the 3 times the transformation. You just would pre-compute it once and then do that. That's exactly the prediction step of the extended of the unsetted Kalman filter. Okay, then the next is use the sigma point, the unsetted transforms, which is the idea of using sigma points and the weights to do the same thing for the observation and to compute the Kalman gain. You can do that exactly in the same way, or at least the beginning can be done exactly the same way. So what do we need to do? Just don't write it down, but at least I want to hear it again. So we had our, so we have to, again, generate new